sometimes, after the surgery, in order to make sure that there is no cancer cell left, usually they do radiation, so radiotherapy, just to kill whatever is left over, or immunotherapy. There are different type of immunomodulators that usually are used, and the last one is chemotherapy, or major one. So usually surgery is the main when in earlier stage, but when cancer cell is big, usually surgery cannot work. So you have to go either radiation, immunotherapy, or chemotherapy. Chemotherapy is very important. The mechanism of chemotherapeutic agents is stopping DNA replication and cell cycle. So that is one thing that, in general term, they interact with DNA and affect DNA machinery. So DNA cannot replicate. Second one is specifically target and inactivate proteins which are present in cancer cells. So this is, of course, the name of the drugs which are used for this specific purpose. And then cancer treatment research usually is a process that depends highly on the understanding of molecular pathogenesis event in cancer. So you have to know the molecular biology of cancer in order to treat the cancer properly. Otherwise, you will make the situation much worse. Mechanism of action and useful chemotherapy. This is a huge table, and don't be overwhelmed by the number. There are, these are different stages of simply formation of a cell. Usually, you have the ribonucleosides forms, and then deoxyribonucleosides, and these form DNA. And then DNA will be transferred to RNA, and RNA make proteins and enzymes and microtubules or whatever. And here, I don't want to go to the detail, but in different stages of formation of RNA and these proteins, different drugs can affect. Suppose a series of drugs like pentostatin, usually what is happening that it affects the enzyme which is responsible for formation of ribonucleosides. If you stop formation of ribonucleoside, it means that you are stopping all these cascade. So cancer cell will die. The same thing, there's another class of compound simply inhibit the pyrimidine synthesis, which is the nucleic acid type of part of it. So when pyrimidine synthesis is stopped, then the whole process will stop, and so on. There's a lot of, I just put it as an example for you to know how many targets are available for us to simply attack and kill the cancer cell line. So this is simply the different type of, and if you like, I can simply make a copy of this as well. But it is should be a literature over here. I forgot, to put that literature. But there is a literature we just simply copied from a literature. So now we understood that most of the cases that if you want to kill cancer cell line by drugs, by medicine, usually we have to simply we have to interfere with DNA formation. So this is a normal, process for DNA formation at the end. The different type of enzymes involved, and this is one section, which is simply this side is got lagging strand, so it's a double strand always DNA. So lagging strand, which is the one which provides all the component of DNA. The other one is leading strand, means this strand will be involved in formation of final DNA, and there are different type of enzymes involved that I don't want to go to the detail. And the enzymes that we will be talking about, and is my target, is called topoisomerase, which what it does, usually it affects the double strand or single strand DNA, and that is the one that I want to talk about here. So topoisomerases, again, are enzymes which are in the last stage of DNA formation are interfering DNA replication. First one is called topoisomerase 1. Topoisomerase 1 only affects the single strand DNA, not double strand DNA. And the way that it is very, very simple. This is a normal type of single strand DNA. Usually topoisomerase 1 comes here. This is serine part of amino acid. usually comes and attack here, break, these two. And then when break these two, well, what is happening that this just circulate, and then when it's just simply move around, rotate around, and then you can get back to the OH from the bottom, come to the top, and then this is forming, and then this OH will attack the topoisomerase. Topoisomerase will be living, and then normal DNA is forming. So this is the way, this is a function of topoisomerase 1, that from one strand of DNA makes another strand of DNA. There is another one by the name of topoisomerase, and of course this is my target. And the reason I am talking about is because topoisomerase 2 is has a major effect on DNA synthesis. So this is a circular DNA, and this is topoisomerase 2. What topoisomerase 2 does, it just comes and remove this one, this yellow one from here, or orange one, whatever you can see it in, by your eyes. I call it orange, somebody call it yellow anyway, whatever. It just, you can see, it comes and cleave, this. So when it cleaves, you can see this portion is open, and this part, this red part, become completely free. So this red part become completely free, and then when it is free, it just simply comes out, and again, topoisomerase 2 is simply getting away from the yellow part, and at the end, what is this is a free topoisomerase 2, and these are two different strands of circular DNA, which is is necessary for formation and replication of DNA. So this is the major, probably those of you who are studying biochemistry usually are dealing with this. So topoisomerase, I use it as a drug target. Why? Topoisomerase is a good drug target because you can see dividing cells require greater topoisomerase activity due to the increased DNA synthesis. So topoisomerase is the most important enzyme in the DNA synthesis. And that's the reason if we stop topoisomerase, means DNA synthesis will be stopped and cancer cell will die. There are two types inhibitors of topoisomerase. I didn't want to put the structures. This is a natural product. Both of them are natural product. Camptothecin, or some, British English, they call it camptothecin, so it doesn't matter what it is. You can pronounce it the way that you want. Inhibit topoisomerase 1, and then doxorubicin is inhibiting topoisomerase 2. So usually what they do, they simply make a complex between DNA and topoisomerase, break, stabilizing that complex, and then DNA cannot, move, cannot be cleaved, and that's the reason cannot replicate. These are, of course, we have different types of topoisomerases. We have mammalian or human topoisomerases, which are topoisomerase 1 and 2 we discussed. And also there are bacterial topoisomerases, which are called gyrase, and also another one which is called topoisomerase 4. It is not written here. So this is for bacteria, but human also. There is some resemblance between bacterial and human topoisomerases. A little resemblance, not much. Now, this is because bacterial topoisomerase has already been studied in detail, and the way that the drugs which are affecting, simply bacterial topoisomerase. This is a bacterial topoisomerase had two subunits, A subunit and B subunit. The active site of the enzyme is in A subunit. This molecule is simply fluoroquinolone. This is a drug which comes in between and then simply interfere with DNA. You remember that we talked that your double strand becomes single strand and again become double strand. This one at this stage, which is a single strand, it stops. So DNA cannot be formed anymore. So that is the way that in bacteria it works like this. In human also work very similar to this. What about cancer? Although a lot of drugs are already available to kill bacteria through interference with topoisomerase, bacterial topoisomerase, but there is no drug available which can inhibit. I mean, in the market, there are a lot of drugs available through the research, but nothing has come to the market. Whatever has already come up to the clinical and still clinical trial and has still have not been introduced to the market is based on this structure. This is a quinolone. We call it quinolone carboxylic acid. And usually the one which kills the bacteria in here, usually in this location, there is a simply alicyclic amine, means type of hexahydropyridine. And here also there is a fluorine involved. So one fluorine and also saturated type of alicyclic system are necessary for making a molecule which can kill bacterial topoisomerase. So they changed this one and they remove fluorine from here and then make the pyridine here, and they came up with a molecule by the name of rosoxacin. Rosoxacin is the first compound from this class which shows anti-cancer activity through topoisomerase. So what they have done two different type of approach to improve the activity of rosoxacin. The first approach is simply changing, we call it peripheral modification, means benzene ring, be substituted with something else. You can say the difference between rosoxacin and this one is just having two fluorine in this location. This is the only difference. Now from here, there is another molecule in which they put in they change the pyridine to hydroxyphenyl. This molecule is also better activity. And then the last one here, you can see hydroxyphenyl and these two fluorine usually are working well. The only difference is, this molecule on the nitrogen has an ethyl, while this one they put cyclopropyl. So putting cyclopropyl and these two fluorine and putting hydroxyphenyl has made a compound which is quite effective as a anti-cancer agent, but still it is working on animal. It hasn't come to human studies yet. That was one approach. The other approach was simply putting substitution on pyridine system. So you can see they follow the same approach from on the top. They put two fluorine and then they put two methyl on the pyridine. So activity is becoming better. And further development of this just simply decarboxylate here. Usually for topoisomerase activity, this beta-keto-carboxylic group is very important because topoisomerases are metalloenzymes. There are enzymes which in active sites they have metal inside, and this chelate the enzymes and chelate the metal and remove the metal from the topoisomerase and make it inactive. So now they wanted to know if this is very important for human topoisomerase. What they did, they decarboxylate this molecule. They decarboxylated and still activity was better. And then the last one, they removed, simply put a substitution which is dihydroxy, phenyl dihydroxybenzyl, substitution. This molecule has a good activity. So this is the way that they started with this molecule and then coming up to this and this, which are active and are used, still they're working on animal models and simply trying to make it as active as possible. Probably I need to, sorry. They need to see me as well. So, so getting to, this information has been taken from current medicinal chemistry. There's an issue by the name of anti-cancer agents. It was published in year 2003, and again, volume 3, number 6, and page 439. This is the literature for all this information.